Okay, so let us start to introduce chapter 20, integrating cells into tissues. Okay, so this graph shows you how the atoms assemble all the way to the organism. Okay, so this chapter we cannot cover the whole process in one chapter. So this chapter will focus on only from step 2 to step 3, how cell form the tissue, such a beautiful pattern or organizing patterns. So it roughly can separate into 2 steps. The first step, individual cell, same type of cell, they can adhere with each other via some kind of cell adhesion molecule or can't. Basically, just some protein will help them to grab them together. So we call those a cell adhesion molecule. So based on that, they can form an aggregation, same type cells aggregation. Then they can form the more complicated structure for the cell junction, which we will introduce later. And also, those cell groups with the cell junction also need to interact with the environment. So they will interact with some protein or some components in the extracellular space we call the extracellular matrix. They are basically the protein or some ion or some different stuff secreted from the cell. Okay, basically the cell just secrete a lot of protein to the environment, and they can form a really compact environment around it, and then the cell will line up those extracellular space. Okay, we call this extracellular matrix. So use this is a kind of enlarged graph of the intestine epithelial cell. So those will be the intestine lumen and this intestine wall. So will be the one intestine epithelial and their neighbors in epithelial cell. They can form really tight interaction between among those intestine epithelial cell. Otherwise, the food or nutrients will go through any space between those cell and to the other cell. They cannot come from a kind of thing we need to observe, a kind of thing we won't need. Okay, right? Okay, so this cell will form a really strong adhesion interface, or called the junction, which we'll introduce later. They need to also form a strong interaction with the bottom environment called the extracellular matrix. Okay, so basically depends on the type. Those adhesion type can classify to cell-cell adhesion, which is the adhesion happening between the cell, okay? Or the cell matrix adhesion, which is which is where it happens to the cell in the extracellular matrix. Okay? So for those cell, basically these are the 4 major cell adhesion molecules, or we call the CAMP in short, and their receptor. Okay, so this is the one cell and their neighbor cells, and this is the process member of this cell and the process member for the neighbor cells. So they will use a lot of different transmembrane proteins. For example, this is cadherin. It will have a short transmembrane domain and a huge extracellular domain, and each of them kind of separated by a lot of calcium binding sites. So each cadherin will bind to the other each cadherin from the neighbor cells. Okay. And this is the IG superfamily or CAMP. They can use those ring rope builder domain to interact with others IG superfamily. Okay. In this case, if the 2 neighbor cells they use the same type molecule to interact with each other, we call this homophilic interaction. Okay, they use an identical type for the effect. We call this homophilic interaction. If 2 molecules use different type of the receptor or those molecular we call heterophilic interaction. For example, this cell uses integrin to interact with one kind of extracellular matrix protein, fibromectin, because they are different. We call it heterophilic interaction. In this case, this protein uses a p-selective interact with some sugar or some glycoprotein. The protein contains sugar. They are not the same protein, same molecule, so we call this heterophilic interaction. Okay? So how such a, for example, the cadherin forms such a homophilic interaction? So as I mentioned before, this transmembrane protein, they can kind of freely lateral diffuse on the plasma membrane. So they will freely diffuse, lateral diffuse on the membrane, and finally they will approach to the other category. They form such a huge complex. So huge complex will interact with the neighbor cells with the those category cluster. Okay, and they have affinity with each other. That is why they kind of can form such an interaction through the mechanism that's really like a Velcro, 魔鬼针, okay, Velcro. Okay, this is Velcro structure on the electron microscopy. They kind of can hook each other. Okay, so those can also hook each other through those Velcro structure. Okay. And for the intracellular matrix protein, we will introduce few part of it. For example, the proteoglycan will be protein. Okay, so the proteoglycan is the protein with the GH, which is the peptide sugar, which we will introduce later. Okay, this is one class of the major group of the intracellular matrix. Proteoglycan and the other is collagen and multi-adhesive matrix protein. So protein or collagen, nominate fibrinogen, nitrogen, intactin will be several major intracellular protein. Okay, we will introduce later. So let just give you some examples of what are those give you a better understanding about the ECM, intracellular matrix. Okay, so this is one example. NAF and HAF are two kind of sponge growing in the wild. Okay, so the sponge cell is really tiny. Those are a lot of sponge cells assembled together and form such a sponge pattern. Okay, this will be other species of the sponge HAF. Basically, in the wild, you can easily tell who are HAF and who are NAF. They grow separately. Okay, they don't mix with each other. But once you use some vortex or some sonication, some we call it mechanical disruption to disassemble of those sponges to become a single cell, and mix two kind of sponge cells in the solution. After a while, they still form the NAF cell, still form the NAF specific cluster. Okay, but the HAF will not form the will not mix with the NAF. So two kind of species, they don't mix with different species sponge. Okay, how can they achieve this? Researcher found this is contributed from their intracellular matrix. Okay, that is what is titled some cell ECM interaction are species specific. So they purify the proteoglycan, which is one kind of intracellular matrix, from the NAF. Okay, those are proteoglycan, one kind of intracellular matrix secreted from the NAF, this sponge. Okay, so they conjugate those purified proteoglycan on the green bits and on the red bits. Okay, then mix these two kind of bits together. This is a plastic, it's 塑胶珠珠, okay, plastic, tiny bowl. Okay, so green bits and red bits all coated with the proteoglycan from the NAF. If you mix that together, then those bits will connect with each other and form such as the green plus the red color will be the yellow color. But if you coat the HAF proteoglycan with the green bits, but coat the NAF proteoglycan with the on the red bits, those two bits will separate with each other. Okay, they don't mix with each other. So that is, they just prove those are the proteoglycan from different species. They don't interact with each other. They only interact with their own species. Okay, so that is why people found some, not all. Okay, some cell ECM interaction are species specific that can help them to find their same species and then can help them to grow and proliferate in the wild. Okay. And also the related density of the cell and ECM different tissues are different. Okay. In this case, it's connective tissue, 结缔组织 connective tissue. Those are pink color are intracellular matrix, and those are purple color are fibroblasts, which is one kind of cell made majorly produce extracellular matrix. So you will see a lot in the connective tissue. There will be huge extracellular matrix protein here. In the connective tissue, there will be huge cellular matrix here, but only few cell here. But in the other, for example, intestine epithelial cell, this is one cell, and the other cell is this dark purple cell nucleus. Very few extracellular matrix you can find between the cell right here. Okay, so they have a different related density. Okay, so if you touch a part of our tissue, you can feel like what's the mechanical property of the extracellular matrix, because they kind of can give you some flexible but still have some mechanical support right over here. Okay, the tip of the nose. Okay, like they can move, but they still give you some mechanical support. Okay. And those cell ECM interaction are important for the development. This is one kind of in vitro system to show you the development process. So you just culture the salivary gland cells into the fibronectin. Fibronectin is one kind of extracellular matrix protein. So if you culture the salivary gland cells into fibronectin, they can form such a beautiful branch pattern. Okay, but if you block fibronectin function by adding incubation with the anti-fibronectin antibody, you cannot see such a normal branch pattern. So basically, antibody masking is one kind of major strategy people use to block the protein. Because when protein need to be functional, they need to interact with their substrate or their signaling partner. Okay, so if you interrupt such an interaction, you will block their function. The protein cannot do the long distance reaction. Okay, there is no such thing. They need to directly interact with their partner or their substrate. So if you use antibody which have a strong affinity to bind with that protein, will cover the whole surface space of that protein. That protein cannot touch their substrate. They will become malfunction. Okay? So that is what anti-fibronectins antibody put in the reaction. They will block the whole function of the fibronectin and such a block, such a cell ECM interaction. And you cannot see such a branch, normal branch pattern. And also, this is also the case. This is the staining of the cartilage in blue and found in red of the wild-type mouse. But if you knock out the collagen 2, which is one kind of extracellular matrix gene, or knock out the prolactin, which is a protein glycan, the other kind of extracellular matrix gene, they cannot form the normal skeleton, and those mice will be kind of visceral. Okay. And also several such as receptor in the ECM interaction will also share regularly several other several signals like what we learned from the chemical ligands. Okay. For example, we learned in receptor tyrosine kinase, and there were several chemical ligands binding to these receptor and trigger downstream signal and regulate cell activity, right? But ECM can also serve such a ligands to bind to such a receptor that can monitor, and also they share pretty similar signaling, and so those binding can also regulate such a cell signaling as well as their signaling, as well as their activity. Okay. So just this is kind of overview in this section. We call the cell and the cell extracellular matrix interaction are critical to organizing and assembling the cell into tissues. Okay, and we also introduced 4 major families. They can form the homophilic interaction or heterophilic interaction. Okay. And also introduce several major components of the extracellular matrix protein. So there, some of such as cell ECM interaction are species specific and important for the development. Okay, so we use a fibronectin antibody blocking and ECMG efficiencies to give you an example. So those are 3 major ECM. Okay. Okay, let us jump to the next section. So now we talk about the cell plurality. Okay. 细胞集径 cell plurality. So once you if you carefully check the composition of the cell membrane, you will see the different sides of the plasma membrane, their composition are different. Okay, they for example, cell will have A side and B side plasma membrane. For example, that is why the cell can do some directional reaction. For example, the cell migration. When cell migrate, there will be a leading edge of the membrane and a trailing edge in the following. Okay, so for example, this is the basically top view from the migrating cell. This will be leading edge. Okay, they will extend the membrane like this, and we introduced last week there will be a lot of development here, so they will migrate gradually from this side, and then will be trailing edge here. So in the trailing, there will be really strong contraction force. Okay, will be a lot of actin here to form the actin ring. They will this will be kind of extend here using microtubule visually. Okay, and also of course it will be extended with some membrane here, but here we have a really strong actin contraction ring. So after contraction, you will kind of move toward the whole cell mass toward the migration direction. Okay, contraction in the back, contraction, and whole stuff will kind of move from here. So as you can see here, the component here and here will be totally different. We call this cell polarity. Okay? Yeah. So it's also the case for the intestine epithelial cell, because intestine epithelial cell, the membrane from this side, they need to absorb the nutrient. The other side, they need to pump out the nutrients. So they need to do a different job. Their composition is different because they have a different protein. Okay? So we call this side will be the apical surface, and this side will be lateral surface, and this side will be basal surface. So I will let you know that the composition of the basal surface and the lateral surface are identical. So usually we just call the basal lateral surface. We don't separate these two surfaces. We just call basal lateral surface and apical surface. Okay? So apical surface and the basal lateral surface, their composition are different. They have two pools of this plasma membrane. One is apical surface, the other is a basolateral surface. Okay. And in different tissue, the epithelial cell will form a different shape. In this case, one layer of epithelial cell they can serve as a barrier, okay, to prevent anything leak from this side to the other side. So they can control what kind of stuff needs to transfer from this side to the other side, or transfer from this side to the other side. Okay, and also this will be also kind of squamous epithelial cell will also do the same job. In some case, they can also form a multiple layer of the epithelial cell. In that case, it can good for some expansion and contraction. They can change the shape. For example, you can find this tissue in the artery bladder. Okay, and also it will be multiple squamous epithelial cell here. It can also prevent some aberrations. Okay, for example, you can see this in the mouth and the vagina. Okay, so this cartoon just gives you the several basic structure of the cell junction. So again, this is the one intestinal epithelial cell, the neighbor cell. Okay, you can see this interior of the cell. There will be a lot of blue colors showing a lot of different cytoskeleton, and this will be the space between the two cells. Okay, a lot of different structure here, complicated structure, or highly organized structure. Here we call the cell junction. So we will introduce them one by one. Okay. So first, you will see the several types of the cell junction: tight junction, angular junction, and gap junction. So the tight junction will be right here, right below the apical surface. Usually, apical surface will come with some microneedles, okay, to expand their surface. So there will be more receptor or more transporter can absorb, capture the nutrients, okay, to increase their surface area. But below, to the end of the apical surface will be the tight junction, okay. So after below the tight junction will be the adherent junction. Then you will see this guy will be the decimal zone. And the gap junction, this will be the decimal zone, and these two are the same. And then also this will be the hemidecimal. We will use this one. Okay? So anchoring junction, there will be three kind of cell junction below to the anchoring junction. One is adherent junction, is this guy. This is tight junction, anchoring junction. And the decimal zone will be here. Okay? And hemidecimal zone will be in charge of the cell matrix adhesion. This adherent junction decimal zone will be in charge of the cell-cell adhesion. Okay? And if you check the electron microscopy, this is the microvilla, will be the apical surface. And the end of the apical surface will be the tight junction. Will be the tight junction. Okay, and below the tight junction will be the adherent junction. Then this will be the decimal zone. It's also called the spot decimal zone because under electron microscopy you will see the one spot here. When you see the dark area, we call that a highly electron dense region. We actually under electron microscopy we don't know what kind of stuff there. We only know they are allowed 30 there. That is why they will show the really dark. The electron beams cannot penetrate that side. We call it highly electron dense area. Okay, so there should be a lot of protein here, and under microscopy there will be one spot here. We call it spot decimal zone. And if you get junction here, sometimes you just need some imagination to tell this is gap junction. I really cannot tell. Okay, tight junction is okay. Decimal zone is okay. The hearing junction, need imagination. Okay. And also, you need to know those junctions will all conjugate with the cytoskeleton in the inside the cell. Otherwise, it cannot deliver such a mechanical information or give enough mechanical support from the inside of the cell to the surface of the cell. Okay? Yeah. It always need to conjugate with some interior cytoskeleton. Okay. So this table just gives you the overview. Adherent junction, decimal zone, hemidecimal zone is belong to the cell-cell, and the cell matrix adhesion type. Tight junction will be the cell-cell. Okay, happen to the between the two cells. Okay, hemidecimal zone is the on the bottom. Happen to the cell and matrix. Gap junction cell-cell. Plasmodesmata is a cell junction in specifically happen to the plant. We will introduce almost in the end of today's talk, today's lectures. So it happens to the cell. Okay, and then will be the principle what kind of major protein in those junctions, which adherent junction will be adherent. Decimal zone will be decimal zone adherent. Hemidecimal zone is integrate. Tight junction will be including protein and gene. And the principal can work in the gap junction will be nexine, and pannexine. And there's defined molecule in the plasmodesmata. Yeah, believe me, those stuff are important. Okay. Oh, usually I don't ask you to kind of remember a different term. I want you guys to know the principle of the mechanism. But this is important. Yeah. Okay. And such adherent junction will connect to the active filament. Decimal zone, hemidecimal zone will bind to the intermediate filament. Tight junction will bind to the active filament. Okay. This they don't know. And the plasmodesmata connect to the active filament. And those is important for the signal, it's important for the mechanical support, blah, blah, blah. Okay, I don't care about this part, but this part is important. Okay. Okay, so we focus on the cap hearing. There's a two kind of cap hearing here. One is decimal zone. The other is adherent junction. Okay, so cadherin are the major self-adhesion molecule in the adherent junction and the decimal zone. So in the decimal zone, it's called the decimal zone cadherin, and they contain. It's right here. Decimal zone cadherin contain decimal gland and the decimal colon here. Okay, and the decimal zone also. The specific structure happens to the decimal zone is they have big solid plaque, or we call the highly electron dense area. Okay, so those are a lot of protein here. They contain glycoprotein. That's more plastic. Glycophilic. There are a lot of protein here. Okay, the electron beam cannot penetrate that side. That is why they show some shadow or some dark area here. Okay, but those plaques only happen to the decimal zone, but not to the adherent junction. Okay? And the adherent junction don't have such a dark cytosolic plaque. Okay, they of course they have some protein. I will show you later, but they don't have such a highly dense protein plaque here. And the cap in the adherent junction, they will be kind of E, N, and P coherent. They also have I showed you before, they have a short transmembrane domain and several extracellular domain separated by the calcium binding site. Okay, and their interaction is totally depends on the calcium. You need to have calcium, otherwise they cannot form an interaction. Okay. So this is the adherent cartoon to describe the composition of the adherent junction. So one cell and another cell, they use each adherent to interact with each other. So they use this transmembrane domain to interact with some adapter protein, for example, catenin or beta catenin. Then those catenin will also bind to the other actin filament, which is the cytoskeleton. Okay. So as I mentioned before, those adherent interaction is a calcium dependent. Without calcium, they can enter. So this will be the example to prove that. So each dot is one cell, and there are a lot of cells here on the microscopy. So if you put the calcium in a medium, culture medium, okay, even these cells have, if they don't have a adherent gene, they cannot form the huge cross-section. They still grow separately. Okay, but if you put the calcium and those cells have adherent, they can form a bigger, those are one cell with a lot of cell cross-section here, because the adherent can help them to interact with each other and assemble them together to form an aggregation. But if you take out, even those cells have an expression of the adherent, but if you take out calcium from medium, they cannot form such a cluster. Okay, so they actually it depends on the calcium. So when in some case when have you guys culture cell? So if you culture cell, you need to kind of see the cell on the bottom of your flask or culture dish, right? There are several ways we can kind of do the subculture. We need to make cell suspension otherwise, and then we can transfer to the new culture dish. This process we call the subculture, because otherwise the cell grow too much. Too many cells grow in the culture dish, they will stop the growth. You need to give them free space for them to grow. Okay, so we need to do the subculture. So how to take out the cell? First, you can add the trypsin. Trypsin is one kind of enzyme, can digest the protein. So you add the trypsin enzyme to the medium, it will digest the protein adhered to the bottom, or majorly the cell attached to the bottom through the one kind of protein called the integrate. You just digest the integrate. So those cells will kind of become suspension, and then you can easily put them and transfer to the new culture dish. Okay, of course you just put part of them to the culture dish, otherwise they grow again, will be super crowded. Okay, that's the one way. The other ways, you can use EGT or EDT, which is a calcium chelator, which will bind to the calcium and block the calcium function. Okay, so without the calcium, a lot of CAM cannot interact with each other, and the cell will easily become a suspension. In that case, you don't need to digest your surface protein. This is especially important for the immune study, because a lot of immune cells, their function totally depends on the surface protein, and sometimes you need to check. For example, a lot of immune cells is a CD4 positive, CD8 positive, a lot of different receptors on the surface, right? Okay, but if you use trypsin or use certain stuff to digest their surface, it will damage their function. So you want to use a viral or not minor ways to do the subculture, then you will use probably EGT or EDT to do this. Okay, so calcium is really important for the adhesion. Okay? So this is just a live cell to show you the real time of adherent junction formation. So this in the beginning, on the steady state, if the cell don't touch with others, the equilibrium just localizes in the whole under the whole parts of membrane. They don't concentrate to the specific site. But once the cell touch with the other cell, they will kind of accumulate to their interface. Okay, and then form the stronger signal here, and finally can form a adherent junction. That is how there's a three-cell kind of sample with each other through and form the adherent junction. Okay, and also such a adherent junction or equicoherent beta-catenin. Equicoherent is the can of the adherent junction. Beta-catenin is a adapter protein for the adherent junction. Those are really important, and people believe these molecules is involved in such a epithelial mesenchymal transition, EMT. So EMT is people widely believe. Some people believe, some people don't. Okay, some people believe EMT is the mechanism for the tumorigenesis. It's the initial step of tumor formation. It's a kind of critical step while the normal cell becomes a cancer cell. Okay, so for the normal cell, they have a good equicoherent, they have a good beta-catenin, they can form a good adherent junction. So that is why they can form a beautiful junction there and do their job there. Okay, but once due to some reason, some cases don't know. For example, they encounter some pathogen attack, they will have some mutant, they kind of exposed to the UV light. Whatever some bad thing happens, and their equicoherent become lower, beta-catenin become lower, and then they don't have a beautiful or organized adherent junction. They become mesenchymal like they cannot form the junction, and they don't stay there. Okay, they become mesenchymal like a cell. So mesenchymal cell is kind of more like a blood cell. They would like to travel inside the cell. They would like to migrate. Okay, but for the epithelial like cell, they kind of form a really beautiful junction and stay there. Okay. Basically, inside our cell has a certain mechanism to prevent these things happening. Once those cells detach from the extracellular matrix, they will trigger apoptosis, and those cells will die. But sometimes bad things happen together. Okay, so you don't have they don't kill off completely. So the survivor cell will become tumor cell, and it becomes such a mesenchymal cell. So on the microscopy, you can easily tell the two kinds of different cells. So this is one cell. The other cell, if this cell adhere to the bottom of the cognitive very well, they will get spread out. They will cross the membrane and then adhere really well, and then you will see the bigger size of the cell. Okay, but if this cell with the same body, but they don't adhere very well, if they try to migrate, they will kind of stand up, and that is why they can migrate faster. If they adhere really tightly, they cannot migrate well. Okay, so those cells will stand up. And so from the top view, you will see the area of those cells become smaller, and then the age of those cells will become brighter. Okay, so those are migrating cells typically. Okay. So people believe this is what happened, as I mentioned before, what happened to the tumor genesis. So under this tumor section, you will see those are tumor cells, and it's also surrounded by some normal cells. Okay, so those are normal cells, and the brown signal are caterpillar. Okay, this is one cell. One cell, you will see the boundary of the line will be brown signal. Those are caterpillar. Those are the junction. So normal cells still have a good equilibrium, have a beautiful junction, but the tumor cell lost those equilibrium and lost their junction. Okay, where there is a equilibrium loss is the driving force. We don't know yet. Okay, there's a controversial study, but people widely generally observe when the tumor cell, when they shift to the mesenchymal-like cell, likely they will become a tumor cell. They will have lower equilibrium benefit. Okay. Any questions so far? Okay, so then let's jump to the tie junction. So as I mentioned before, the tie junction will be the end of the apical surface. Okay, they form such a zip-like structure and make such a space really tight with each other. Okay, so they can help. They form tight enough, super tight enough, even tighter to prevent the electron diffuse of the membrane component. That is why the apical component or apical lipid apical protein can only electron diffuse in the apical site. Once they approach here, they cannot cross those effectors and go to the other side. Okay, so tight junction will be the guide to separate the apical site and the basolateral site. If your tight junction dysfunction, there will be no apical site and the basolateral site. And then your epithelial cell cannot do such a good nutrient transportation work. Okay? And also, it will form really tight here, so that is why small molecule cannot really, the molecule cannot really cross this area, extracellular space area. Okay? So, of course, those tight junction, they are kind of built up by the protein. Those still have some space between those protein. Okay? There are several major camp of the tight junction grounding in the protein. Okay? They will use their extracellular space, extracellular domain to form such a camp interface. Okay? But there's still some pool. But only super tiny molecule can penetrate that pool. The molecule smaller than 0.8 nanometer still can go across that tiny pool. Okay. And also, the junction adhesion molecule gene will be also the major can you can find in the tight junction. Okay. And then also, in some cases, tricellular is the protein concentrated on the junction where the 3 cell intersect. Okay, 1, 2, 3 cell intersect. Okay. And how to prove that tight junction is the major structure to prevent molecular leakage between the lumen side and the lower circulation side. So people can dig this experiment. They just inject one leucine hydroxide, which is an electron-dense colloid with a high molecular weight. So under electron microscopy, they become really dark. Okay, so they just micro-inject this electron-dense colloid into the circulation system, so they will feel diffuse to everywhere. And under microscopy, you will see, the leucine hydroxide can diffuse to the space until they approach to the tight junction. They cannot cross the tight junction. Okay, so tight junction can is the structure. The adhesion junction cannot prevent this, but tight junction can. Okay, they can prevent the free diffuse of those high molecular weight stuff to prevent any leakage between this side and the other side. Okay, so this tight junction is the structure to determine the apical surface and vessel membrane. It's the guide to determine the cell mortality. Okay, and it also prevent if the molecule transport through the paracellular pathway, through this extracellular space, we call this paracellular pathway. So only small molecule, certain ion can kind of transport through this paracellular pathway. Okay, if the molecule transport through the cell, we call this transcellular pathway. Okay, so through the transcellular pathway, several transporter can kind of specifically absorb the nutrient or their essential molecule and then deliver to the site, to their destination. Okay, so I would like to ask you one question. So as I mentioned, based on the definition, that the membrane protein and the lipid in the apical side and the basolateral side are different, right? How to prove this? How to prove this? If I ask you to design an experiment to prove this, how to do that? Okay, I will include this in the test. Okay. It's easy. Just think about. Okay. Yeah. Can you understand my question? how to prove apical the basal layer have different lipid composition and protein composition. Okay, so let us jump to the gap junction. So gap junction is permeable to the molecule as large as 2 nanometers in diameters. Okay, so several molecules such as cyclin AMP, IP3, calcium, those are small molecules, they can penetrate, they can go across those gap junction. Okay, so this is the monomer of the gap junction. The major chem of the gap junction is called connexin. So this is the monomer of the connexin. Okay, so the connexin have a 4 transmembrane domain. Their structure looks like a slice of pizza. Okay, and one cell will contribute for 6 slices of the pizza, and then we will bind to the other 6 slices of the pizza from the other cell. Okay, they can form such an entire conduct. Okay, so in the understand state, usually they close. Okay, they don't have a tunnel in the core, but with some post-translational modification, this means the modification happens once after they synthesize. Okay, we call it post-translational modification. Modification happens to after protein translation. Okay, so for example, phosphorylation. If you add some phosphate group to those proteins which change their conformation and they will twist with each other and generate such a space in the core region, that will be the conduct or the tunnel, allowing small molecules to go across this area. Okay, so it's good for the 2 nanometer molecule to go across. Okay, so that is why. So such a phosphorylation and dephosphorylation, I mean, add the phosphorylated group and take a phosphorylated group can be really fast, like a millisecond scale. Only 0.1 second, you can add phosphorylation or take out phosphorylation. Okay, so that is the mechanism cell usually used to switch their reaction or change the protein formation. So such an open-ended process could be really fast, okay, and can be precisely controlled. Okay. So in this section, we talk about the cell plurality. There will be kind of apical surface and the basolateral surface, and the tight junction, which can kind of connecting cells, can serve as the diffusion barrier of the epithelial sheet, can maintain the cell plurality, which determine the apical surface and basolateral surface. The major chem of the tight junction is including carotene and gems. Okay, and molecule can transfer across the epithelial cells through the paracellular. Only small molecule can go through the paracellular. Molecule smaller than 0.8 nanometer in diameter, or the molecule is smaller than 200 delta. Okay, which is really small. Okay, and the transcellular pathway can large molecule or specific molecule can only deliver through the transcellular pathway. Then a lot of transporter need to absorb and deliver to the other side. Okay. In the gap junction, molecules smaller than 2 nanometers can diffuse across the gap junction, and its major components connect those are slices of the pizza. Okay, and the phosphorylation can change the conformation of the connexin and open the tunnel of those gap junction. And the interjunction will be kind of including adherent junction, desmosome, and hemidesmosome. We haven't introduced about hemidesmosome, we will talk about it later. Now we only cover the adherent junction and desmosome. So the 2 different categories such as desmosomal category and classical category are the major component of those desmosome and adherent junction. And the biggest difference between these structures would be kind of desmosome contains a plasmid plaque, okay, but adherent junction don't have such a plaque, okay. And loss of the E-category may induce EMT, epithelial mesenchymal transition, which may cause a tumor formation. Okay, any questions so far? No. Okay. Okay, so we finished the cell junction. So next we go deeper. Okay, so we introduced about this part, orange. So next we just go deeper. So now we talk about the extracellular matrix. So the first layer of the extracellular matrix will be the basal lamina. Okay. So if you on the electron microscopy, this will be the epithelial cell. So those are mitochondria, nucleus. This this area is in the extracellular matrix, and this layer sheet will be the basal lamina. Okay. They will be the first layer of the extracellular matrix area. Okay. So if you freeze the sample and then take out the cell, sometimes some plasma will retain on the surface of those basal lamina. And if you view from the observe the plasma membrane from the inside of the cell, you will see just observe from this side to this plasma membrane, you will see part of this basal lamina structure. They kind of will be the mesh work, really complex mesh work. Okay, that kind of network. Okay, structure. So the basal lamina is important for a lot of different things. Okay, basically just organize cell, organize tissue. And also the important function is they can also serve as a diffusion barrier. Okay, there's a really important diffusion barrier. Of course, it's also the barrier to prevent, in addition to the tight junction, those basal lamina will be also important to prevent the molecule traffic from this side to the other side on the epithelial intestine wall. Okay, and then in the brain, there will be kind of barrier called the blood-brain barrier (BBB). Okay, that's also important stuff. Okay, so our brain is only about 2% weight of our life, but it's highly energy demanding. It needs 20% of the total energy. Okay, so the energy mainly comes from the circulation. So that is why a lot of blood vessels can be found in the brain. Okay, so if you enlarge those blood vessels, so let me draw the structure of the blood vessel. So blood vessel, this is the lumen of the blood vessel. The first layer of the blood vessel will be one layer of the cell called the endothelial cell. Membrane. Okay, and then it will come with basal lamina. Here, this is lumen. Okay. And then we have some smooth muscle cell fibroblasts here. Okay, but for some temporary blood vessel, it's only have endothelium that they don't have a big blood vessel wall. Okay, so in here, these are the section of the blood vessel. You will see the endothelium cell here. Okay, what is so those are vessel lamina will be here, and outside here will be some neural cell, which means a brain. Okay, so those basal lamina are they contribute to the one important barrier called the blood-brain barrier, which separate the environment here and here. Okay, only very tiny molecules, for example, some nutrients can cross this area and go into the brain. Okay, so this is really what the people found is when they try to treat some drug to the brain disease. Okay, for example, some chemotherapy drug can easily kill the tumor happens to not organ, like liver cancer or kidney cancer. But when they try to kill the tumor inside the brain tumor, they use the same drug. Those drugs cannot really go across this BBB and they cannot touch the tumor in the brain. They cannot kill the brain tumor. Okay, so the BBB will be the guys you need to kill when you're trying to apply some drug to the brain area. Okay, and also there are some drugs where we can deal with some neurodegenerative disease or some proliferation, I don't know, repairing. Okay, such stuff. You all need to deal with such a blood-brain barrier. Okay. Of course, there are some ways now people can temporarily open this BBB. For example, you can use a really strong ultrasound. Give some mechanical vibration, they can open the BBB temporarily. So after just one shot of the ultrasound, it can temporarily open. After 4 to 6 hours, they can seal. Okay, so you have a kind of 6 hours window to deliver drug, and they can do that locally because ultrasound can be focused and deliver acoustic pressure to only the region you're interested, for example, the children. Okay, so you can kind of deliver locally deliver drug based on that. Yeah. Okay. So, so inside, so now that we talk about evidence model, which is the junction happen to the cell and the basal lamina. So it's the major camp of those hemidesmos is integrin. Okay, integrin is also the major protein which helps cell to adhere to the bottom. Okay, so integrin are all heterodimer. They were formed by the alpha fold and the beta fold, and with a different combination. For example, it will be alpha 1 beta 1, alpha 2 beta 1, alpha 3 beta 1, alpha 4 beta 1, blah blah blah. I will not ask you to remember all of this because I cannot remember either. Okay, you just need to know there will be alpha 4 and beta 4, and with a different combination, they have sometimes different function. They will interact with different component. Okay, and there are three amino acid combination will be their kind of super. They will super like to interact with the three amino acid. With RGE domain, arginine, glycine, and aspartic acid. Okay, it's super love to interact with such as three amino acid. Okay, for example, 5-10 they contain several RGE domains, so that is why integrin will bind to the 5-10. Okay, and as I showed you before, this is the EN graph of the basal lamina, right? And this is the ketone of those network. Okay. So there are several major components of the basal lamina. Laminin, nitrogen detected in the type 4 collagen and the polymer. Okay, basically the key concept here is those guys provide a lot of binding site. Those binding sites allow the cell to bind itself. Okay, to do the self-assembly. They can also provide a binding site for other people to bind it. So they will bind with each other and bind with others. Finally, they can form a really strong interaction and form a really compact network to provide such a diffusion barrier and also provide a mechanical support. They are another binding site. That's it. Okay, that will be the major concept we need to remember. Okay, for the laminin, okay, which under microscopy you will see this cross. They have a three amino polypeptide. Chain will be an alpha, beta, and a gamma chain. Okay, 1, 2, 3. And again, I would not ask you, for example, this globular domain will bind to who? This globular will bind to no, I can't remember it. Okay, you just need to remember they can bind by themselves. They can bind with others. That's it. That will be enough. So that is why they will interact with each other and form a strong interaction. Okay. And finally, provide another mechanical support. Okay, and the collagen, all collagen are trimetric protein. Okay, this is the one polypeptide of the collagen. So 3 polypeptide will rand up and assemble to the thinner collagen fiber. Okay, and those are collagen. If you check the amino acid sequence of the collagen, you will find a lot of repeat of this three amino acid: glycine, X, Y. Okay, X, Y can be any amino acid, but they're often proline and hydroxyl proline. So you will see a lot of glycine, X, Y, mostly glycine, proline, and hydroxyl proline. Okay, because they rand up really tightly. So in the center area will be super crowded. If you use a top view, this lumen will be really crowded. So with a limited space. So they usually will arrange the glycine in the center because they have the smallest side chain, just proton. Okay. So they put the glycine which have the smallest side chain in the core region. Then the glycine, then you see XY glycine, glycine. Okay. That's what it's on. And the glycine has a 3 trimeric. So you will see different collagen have either two alpha one alpha two, or three alpha one, three alpha one, three. I cannot remember this either. I will not ask you to remember this. It's meaningless. Okay, unless you study collagen, you need to remember this. Otherwise, you don't need to. Okay, you just remember collagen has three polypeptides. One day, if you study collagen, you can check this table. There will be no test at that time. Okay, don't waste your brain to remember this. Okay, it's meaningless to me and to you. Okay. And those collagen, they can form a triple helix, and they have to the N-terminal and the C-terminal, and they will be globular domain. Why you call it globular domain? Because under the microscope you see such a bubble-like pattern. So those globular domain can interact with others. Okay, they interact by themselves, they interact with others. That is why they can form a network. Okay. So finally, they can form such a network and interact really with a complex interaction, and finally can show such a strong physical property of this sheet-like structure called vessel. And we also we're talking about the polycane. So polycane is kind of a glycoprotein. It's a protein conjugates sugar. Okay, so this is basically one kind of there are several kind of sugar. There's an unlinked sugar, olic sugar, or GAG, which stands for glycosaminoglycan, which are non-polymer repeating disaccharide. Two sugar, repeating two sugar. We want to use that. Okay, we call this a GAG. So the protein conjugate with GAG, we call this a proteoglycan. It's one kind of glycoprotein, proteoglycan. Okay, so here the amino acid we will call that core protein, and those are sugar, repeating sugar, GAG, we conjugate with a certain amino acid. Whole things we call the proteoglycan. Okay, so polycane is one kind of this proteoglycan, and it also have a lot of binding site. They can bind by themselves, they can interact with others. Okay, and also finally form such a vessel. Okay, so in this section, we talk about vessel amino as a sheathing meshwork of the ECM components. And basically, those are protein mainly synthesized by cell. The cells generally they just synthesize those proteins, secrete out to the extracellular space, and they can kind of form with each other and assemble to such a sheathing meshwork. Okay, that is where it comes from. And also we talk about collagen. Collagen are trimeric protein. They contain many repeated glycine XY repeats, and the interaction between the globular domain that help them to form a network. And the polycane is one kind of glycoprotein. They contain the three kind of polysaccharide, namely omega and GNG. Okay, and also polycane can bind to other ECM molecules. And nitrogen, we don't introduce much, but basically it also interacts with others. Okay. Laminin is a cross carbon structure. Is a hetero-trimeric protein. It contains alpha, beta, and gamma chains. It also can self-assembly and bind to other molecules. And finally, they can form such a compound and with a strong mechanical support of the mesh work. Okay. Let us take the 5-minute break, then we will introduce the following section.